Consider this relation L, which is a set of all A, B, and R2 such that A is less than B. You should be able to check with yourself that this relation L is reflexive and transitive but not symmetric. It's actually not symmetric in a rather extreme way because, there's a lot of real numbers A and B where A is less than or equal to B, but B is not less than or equal to A. And in fact, it's so not symmetric that if you have two numbers A and B where A is less than or equal to B and B is less than or equal to A, then it immediately follows that A is equal to B. And in general, if we let A be just any set and R be a relation on that set, then we call R antisymmetric. If and only if, for all x and y in A, if x is R related to y and y is R related to x, then it follows that x is equal to y. And the motivation for why we call it antisymmetric is that R is so not symmetric that there cannot be any two distinct elements that are inversely related to each other. So R is like the opposite of symmetric, hence antisymmetric. So for example, if you let A be any set and let S be the set of all x, y, where x and y are in the power set of A, such that x is a subset of y, then x is reflexive, since for any set x is a subset of itself, and x is transitive, as we can see here, and S is also antisymmetric, since if x and y are distinct sets, then it cannot be the case that x is a subset of y and y is a subset of x. So x and y must be equal. This is why this is antisymmetric. Intuitively, both S and L are relations that tell us how we order elements in one direction in the power set of A and in the real numbers respectively. So for example, the way we order things in S would be we would have a set X, then a set Y coming after it if X is a subset of Y, and the same thing for L if X is less than or equal to Y. And in general, if you let A be any set, R be any relation on that set, then R is a partial order on A if and only if R is reflexive, transitive, and antisymmetric, and R is a total order on A if and only if R is a partial order, and for all x and y in A, either x is R related to y or y is R related to x. So the motivation for the definition of a partial order is all about relations telling us how to order things in one direction. So we want such relations to be reflexive because when you're doing stuff with reflexive stuff, it just becomes easier, and it's how we define antisymmetric. And we want it to be transitive because if we have, for example, three elements or three objects, A, B, and C, that come in this order in a direction, then B comes after A and C comes after B, so C comes after A. This is why we want it to be transitive. And we want it to be antisymmetric because let's say we have A, B, and B, A. This totally and completely ruins the thing we're trying to do with relations that tell us how to order in one direction. Because let's say this is a direction, but this is also a direction. So these are two directions, not one direction. And it's called a partial order because not every element of A needs to be ordered in R. That's what the word partial comes from. And that's where total order comes from. Because total orders order everything in this the set that R is a relation of. So let's go back to the relations L and S we just considered earlier. Both of these are partial orders because, we've already shown that they're reflexive, transitive, and antisymmetric. But only one of them are total orders, which is L. S is not a total order because, if we just let, A, B, 1, 2, then both the set of 1 and the set of 2 are in the power set of A, but none of them are subsets of each other because, they're disjoint. So in other words, S gives us a way to compare two sets that are not disjoint, but L gives us a way to compare any two real numbers. So for a last example, let's let D be the set of all AB, where both AB are positive integers such that A divides B. Now we can ask, is D a partial order or a total order? Let's see. It's pretty easy to show that D is reflexive because any positive integer A divides A, because A on A is 1. Is D transitive? Let's see. D is transitive if and only if AB is in this set, D related to B, and B is D related to C. What the hell is that? D related to C. Then A is D related to C. So A divides B is the same thing as saying B is divisible by A, and same thing with C is divisible by B. So this is true if and only if B is NA and C is MB, where N and M are positive integers. Since B is NA, we can replace this MB with M and A to make C equal to M and A. And since M and N are positive integers, then their product will also be a positive integer. So this means that C is divisible by A, and A divides C, meaning A is D related to C. So we know that this relation is also transitive. But is it anti-symmetric? Well, let's see. So first, suppose that A is divisible by B and B is divisible by A. And this is only true if and only if A is NB and B is MA, where N and B are integers. Since B is MA, we can replace this NB to make A is equal to M and not B, M and A. And this is only true if Mn is equal to 1, or M is the reciprocal of N. And since M is an integer, what you'll notice is that if N is anything besides 1, then 1 on N is not an integer. But if N is 1, then it is an integer. So that means N has to be equal to 1. So if you plug in A equals NB for 1, A is 1B, so A is equal to B, meaning this relation is anti-symmetric. So we get that this relation is a partial order. But is D a total order? Well, let's see. Suppose we have an ordered pair AB, where A and B are positive integers, and we let A and B be both prime numbers. Since they're prime, none of them divide each other. So we get that A is not D related to B, and B is not D related to A. So that means this is not a total order, since this doesn't work for any prime numbers. Now let A be the set of all English words, and R be the set of all A, B, and A2 such that A appears in the same order in B. So, for example, the rap is R related to rapper because rap appears in the same order in the word rapper. But it is not true that rapper is, why did I put a D? R related to rap, because rapper does not appear in rap. So R is reflexive because, for example, rap is R related to rap because rap. I hate saying rap so much. Let's do a different word. Let's do like can. Can is R related to can because can appears in the same order in the word can. Rap. 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 And we'll also see that R is transitive because, for example, can is R related to cannot, and cannot is R related to cannot. Just assume that cannot is an English word. So if this is true, then can is R related to cannots. And R is anti-symmetric because, like, I don't know, bro. Obviously, like, proof is left as an exercise to the reader, bro. Holy cow. Anyway, this means that R is a partial order. Now consider this at B, which contains in, index, into, and in. And this is also a subset of A. And what you'll notice is that one of these elements, specifically in, is R related to every single element in B. If we interpret the statement R is, X is R related to Y as the same thing as saying Y is at least as large as X, then in some sense we can say that in is the smallest element of B, since it's smaller than every other element in B. Now consider this news at C, which just contains all the words in B, but I just added an O. Wait, O isn't a freaking word? What am I doing? A. There we go. And what you'll notice is that neither A nor in are larger than any other element in C, using larger as in what we mean, like how we used it before. So since neither A nor in are larger than any other elements of C, then we'll call we'll call A and in minimal elements of C. But note that neither A nor in is the smallest element of C, because first of all, A is not contained in anything in here, and in is contained in index, into, and in, but not in A. So it's not smaller than every other element in C. So the set C has two minimal elements, but no smallest element. You may ask if a set like this can contain more than one smallest element because of these nuances that I'm pointing out, and we don't know that answer yet. So until we figure that out, we'll just refer to, so let's say A is the smallest element of A. We'll refer to A as a smallest element of A, not the smallest element of A. Because if it was the smallest element, that would imply that there's only one smallest element, and we don't know that yet. And to figure that out, we should actually define what the hell I mean by smallest and minimal. For this definition, suppose A is just any set, and R is a relation on that set, and also let B be a subset of A, and let C be in that subset B. And we'll define C to be an R smallest element of B if and only if for all X and B, C is R related to X. And we'll define C to be an R minimal element of B if and only if there does not exist an X and B such that X is R related to C and X is not equal to C. So the motivation for this definition is the fact that, again, R gives us a way to order the elements of A in one direction. So suppose it implies that the order goes like A, B, C, D for distinct A, B, C, and D. Then we would consider A to be the R smallest element of this set, because A comes before B, C, and D. And the motivation for R minimal comes from the fact that, for example, here, A does not come after anything in this set. So A would be an R minimal by the definition. So for example, let L be the relation defined before, and B be the closed interval from 7 to infinity. Does B have any L smallest or L minimal elements? Let's see. So an element A would be an L smallest element of B if and only if for all X and B, A is less than or equal to X. And if we let A be 7, then we find out that 7 is an L smallest element of B, since 7 is in B and 7 is less than or equal to everything in B. And we can figure out that B only has one smallest element because let's say 7 plus epsilon is in B. No matter what epsilon is, 7 is less than or equal to 7 plus epsilon. So there exists a real number in B that is less than or equal to 7 plus epsilon. So 7 is the only L smallest in B. And an element A of B is L minimal if and only if there is no other distinct real number in B that is less than or equal to A. And again, if you let X be 7, then find out that 7 is also an L minimal of B. And 7 is also actually the only L minimal of B. Since, again, let's say 7 plus epsilon is in B, then 7 plus epsilon and 7 are distinct, and there exists a real number in B that is less than 7 plus epsilon, 7. So we find out that B only has one L smallest and one L minimal, and that is 7. But now, instead of a closed interval for B, what about if we make it open? Then in this case, B does not have any L smallest or L minimal elements. This is just a consequence of the continuity of the real number line. So let's assume that this number 7 plus epsilon is the L smallest element of B. Then, in a way, 7 plus epsilon is the first number in this interval when ordered using L. So in a sense, this means 7 plus epsilon is the next number after 7. Well, if this is the next real number after 7, let's see what happens if we divided epsilon by 2. Since epsilon is a real number, we can divide it by 2, since any real number is divisible. Or not divisible, what the hell am I saying? You can divide any real number by 2 and get another real number. What we get is a number less than 7 plus epsilon. And in fact, we can divide epsilon by any real number, n. So there is no L smallest element of B. This is actually the same reason for why B does not have any L minimal elements. And now, since we have defined smallest and minimal elements of sets, then we can finally answer the question and a couple other questions, including, does a set only have one smallest element? And this theorem says that no. If B has a smallest element, then that smallest element is unique. For this theorem, suppose that A is any set, R is a partial order on that set, and B is a subset of A. The first, well, we already went over that. The second statement says that if we let E be the smallest element of B, then E is also the only minimal element of B. And the third says that if B is a total order and M is a minimal element of B, then M is the smallest element of B. To prove the first statement, well, first we'll have to let E be the smallest element of B. Then we'll assume E1 is also a smallest element of B. And of course, E1 is not E. Then this is true if and only if for all x and B is are related to x, and for all x and b, E1 is R related to x. We'll just join these universal quantifiers together to get that this is true if and only if for all x and b, E is R related to x and E1 is R related to x. Since both E1 and E itself are in B, we get that E is R related to E1 and E1 is R related to E. But since R is a partial order on A, then that means R is antisymmetric, which means this cannot be true. This means, since R is antisymmetric, that E is equal to E1. And since we have E equals E1 and E is not E1, then the assumption that there could be a distinct element in B that could also be a smallest element is not true. That cannot be true. So this means that E is the smallest element in B, not A, smallest. Now to prove the second statement, we'll first suppose that B is the smallest element of B. We're trying to prove that B is a minimal element first, so let's assume that B is not a minimal element, which implies that there exists a BO in B, where BO is R related to B. and BO is not B. Again, since B is the smallest element, it's guaranteed that B is R related to BO, and we just assumed that BO is R related to B. And since R is antisymmetric, BO has to be equal to B. This leads to a contradiction, so there does not exist a BO where this is true, meaning B is also a minimal element of B. Now to prove that B is the only minimal element, well again you do contradiction, and we'll assume that there is some BO in B where such that there does not exist an X in B such that X is R related to BO and X is not BO. Well, since B is the smallest element of B, then we know that B is R related to BO since B is in BO is in B. So this means BO is not equal to B. But since there does exist an X in B where this is true, that means that leads us to a contradiction, meaning there does not exist anything else in B that is also a minimal element. So we got that B is the only minimal element. And finally, to prove the third statement, we have to suppose that R is a total order on A and B is the minimal, or is a minimal element of B. So using the definition of these terms, we can get that this is true if and only if this is true. And again, we'll use contradiction, so we have to assume that this is in existence. We have to assume that B is not the smallest element, which is true if and only if not for all X and B is R related to X. And this is true if and only if there is an X in B where B is not R related to X. And if this is true, then this R being a total order cannot be true, because since there is no X in B that is R related to B, that is not B, then this one is immediately crossed out. And since this is true, then this is not true for all elements in B. So you reach yet another contradiction, meaning since the statement that led to the contradiction was B is not the smallest element of B, then that means B is the smallest element of B. When comparing and working with subsets of some set A, then we use what's called the subset partial order, which is this partial order on the power set of A. From the definition we gave to smallest elements of subsets, if we let F be a subset of the power set, or this just means that F is a collection of subsets of A, then we say that a set X is the smallest element of that set if and only if it is a subset of every other element in the set. This is what mathematicians usually mean when they say like smallest set, that they're using the subset partial order on the power set of the set. So for example, if you let X be a subset of the real numbers and let 5 be in that set X, and say we want to find the smallest set of real numbers X that satisfy this property, where for all X and Y and R, if X is an element of X and X is less than Y, then Y is also an X. Even though we haven't specified the partial order we're using to define smallest, and what we mean by smallest set in this case, even though we haven't specified it, it's assumed that what we mean by smallest, we mean smallest in relation to this partial order, which is what we called earlier the subset partial order on the power set of the real numbers. So to solve this problem, first need to realize that X is at least the set of 5. And since 5 is an X and 5 is less than every real number that is greater than 5, then this means that this also must contain every real number from 5 to infinity. So what we get is that the smallest set that satisfies this, or a small set of real numbers that satisfies this, is the closed interval from 5 to infinity. Now what about this problem? We want to find the smallest set of real numbers X that is non-empty and satisfies the property where for all X and Y and R, if X is an X and X is less than Y, then y is an x. And this would be really easy to answer if we had a clear starting point where x is at least as large as some set that contains some number, and just do what we did in the last problem. But here, that is not clear. It's only clear that x is non-empty. And in fact, there is no smallest element that satisfies these properties. Suppose we had the interval from earlier, or from last problem, closed interval from 5 to infinity. Yes, this interval satisfies these properties, but it is not the smallest because, for example, 6 to infinity is smaller in the sense of the subset partial order. But this is also not the smallest because there's also 7 infinity, and you could just keep going, like a million infinity. That's 100, what the hell? And you can just keep doing this until you reach the end of the real numbers, which doesn't exist. So this has no smallest set that satisfies this. At this point, you've probably guessed how to define largest and maximal elements of sets, and you would probably be right because it's pretty easy. If you let A just be any set, R be a relation on that set, and it's a partial order, and let B be a subset of A, then B is the largest element of B, if and only if for all x and B, x are related to B, and B is the maximal if and only if, or B is a maximal if and only if there is no element of B where B is R related to that element that is not equal to B. So for example, if we let A be the natural numbers and B be the set of 1, 2, 3, subset of A, then let R be the set of all A being N2 where A is less than or equal to B. Then in B, 3 would be the largest element because every other element is R related to 3 in B. And 3 would also be the only maximal because there is no element of B that isn't equal to 3 that 3 is R related to. Another really useful concept regarding this is a concept of lower and upper bounds. So if we define R, A, and B as before and let C be an A, then C is a lower bound for B if and only if for all x and B C is R related to X, and C is an upper bound for B if and only if for all x and B X is R related to C. And what you'll notice is that the definition for a lower bound and a smallest element looks really similar. That's because the only difference here is that C is an element of A. It does not have to be an element of B. So now we can say that a smallest element for a set B is just a lower bound for B that's also in B. So for example, if we go back to what we did earlier with the less than or equal to total order on R, and we let C be the open interval from 7 to infinity, then we said that there is no smallest element, or there is no L smallest element in C, but there is a lower bound for C, and that is 7, and that's because, again, 7 is L related to everything in C, or 7 is less than or equal to everything in C. And in fact, in this case, 7 is what we call a greatest lower bound for C, meaning that if we let some set L, let's just rename this freaking thing, bro. If we let some set L be the set of all lower bounds, then 7 would be in L, and 7 would be the greatest of this set according to this relation. So we would call 7 the greatest lower bound, or just we could abbreviate it with GLB, greatest lower bound. But now suppose we changed C to be the open interval from minus infinity to 7. Then what is 7? Well, 7 is an upper bound for C according to less than or equal to. And in fact, 7 is what we call a least upper bound. And what that means is if we let U be the set of all upper bounds, then 7 would be in U, and 7 would be the smallest element of U. So we could abbreviate, that looks like a greater than or equal to, we could abbreviate 7 to be LUB, standing for least upper bound. So for example, if you let L be the less than or equal to total order on R, and let B be a subset of R, that is the set of all 1 on n, where n is a positive integer, then does this set have any lower or upper bounds? Does it have any GLBs or LUBs? Well, let's see. Well, some element c, that's a real number, be a lower bound, if and only if for all x and b, c is r related to x. Or let's change this to c is less than or equal to x, because that's the definition of L. Well, we'll just rewrite b as the set of 1, 1/2, 1/3, and so on. Does there exist a real number that is less than or equal to all of these? Yes. And that real number would be 0. And in fact, 0 is actually the greatest lower bound of b. Well, does this set have upper bounds? Yes. One of them is obviously 1. And the set of all upper bounds of b would be the closed interval from 1 to infinity, because every element of b is L related to every element in this interval. And in this interval, 1 is obviously the smallest element, so that would mean that 1 is the least upper bound for the set b. 1 is least upper bound. And an important fact about this example is that even though b does not have the smallest element, it does have a greatest lower bound. This is actually not a coincidence. This is not specific to this, example. Because it's actually an important fact about the real numbers that every set of real numbers that has a lower bound has a greatest lower bound. Similarly, every set of real numbers that has an upper bound has a least upper bound. But the proof of that is way beyond the scope of this video, because that's like real analysis and stuff. And this is actually a really special fact about the real numbers, because this doesn't even apply to even all total orders. So that's what, I mean, there's a lot of special stuff about the real numbers. I'm not going to get into it. So to answer the question in the title and thumbnail, what comes after 4? Well, honestly, it just depends on which order relation you're using. Because if you were using the less than or equal to total order on R, then there are an infinite amount of real numbers that come after 4 using this. But for example, if you restrict it to the natural numbers, then yes, what comes after this is 5. Because 4 is less than or equal to 5. If we're using the greater than or equal to partial order on n, then what comes after 4 is actually 3. And actually, if you were still using the less than or equal to total order on R, then what comes after 4 could be 5, but it could also be 10, or 1,000, or 10 to the 100 to the 10 to the 100 to the... You get the gist. So the answer is, since it depends on the order relation you're using, the answer is every number comes after 4. Anyway, goodbye.